in 1993, I attended a field trip from Kathmandu to Lhasa, and I worked in the Tibetan side of the Himalayas, and I was fascinated by the landscape, by the geology, and by the people living in the Himalayas. So after that, I worked many, many, many times. I attended many field trips in the Himalayas, and I worked a lot in this very nice continent. So I am very happy to be here, and I will show you some research result, some topics about the Himalayas and the other origin in Western Europe, because I worked also in the Alps, in the Apennines, in the Variscan belt of Europe, and the old origin, the Paleozoic origin, and also in the Transantarctic mountain. I was in Antarctica 6 times to work in the Transantarctic mountain to make geological map and tectonic studies. So I will show you some result of this long experience because I'm quite old. And I hope that this course will be useful to you to understand a little bit better the orogenies, the Himalayan origin, and some topics of structural geology. So if you have a question, please ask me. No problem. You can interrupt every time when you need. So I hope this this course will be useful. Okay. So as a reference book, I suggest you these two books to go into depth structural geology. The first one is structural geology from Akun Fossen. It's a very nice and modern book. There are also a lot of resources on the web, e-modules, e-charts, movies from the book, so you can enjoy a lot using this book. And this one, Microtectonics, is by Pacher and Trau. The second edition is not 2025, 2005, not 25. But it is very useful for the microstructure because it is the best book dealing with this topic. Okay. So if you need, I have a PDF copy of this one, of the macrotectonics. I can share with you. Okay, in the first day, I will give an introduction to origins and orogeny, a little bit recall the Wilson cycle, classification of origin, and the architecture of an origin. Uh, are you from bachelor, master courses? Master studies. So you have a little bit knowledge of, okay, thanks. Because it is not easy to explain to a public without knowing. Okay, so an origin is a region of the Earth crust that has been deformed and uplifted through compressional tectonic processes, leading to the formation of a mountain belt. As you know, the Himalaya you have just here, you know very well what is. Uh, it typically includes folded and faulted rocks, metamorphic zones, igneous intrusion formed during an orogenic event, mountain building episode. We will speak about the Himalayan origin, of course, the Alpine origin. There is 1 hour devoted to the tectonics of the Himalayan origin, and also the Variscan origin, that is the Paleozoic mountain popping out in Western Europe, and also, of course, in Italy. Okay, orogeny is a set of processes and phenomena that led to the formation of a mountain range. This uh, satellite view of the Himalayas on the right. You can see the Mount Everest group. Sorry. Vabbè, non ci sta. Okay, and there is a distinction in literature in between orogeny and tectogenesis, because one is referred to the uplift of the mountains, and the other terms is referred to the overall processes. But now with orogeny, we include all the processes leading to the formation and uplift of the mountain. So in the book, in the literature, you can find this differentiation, but orogeny is the best term to use. Okay, a mountain range is due to crustal shortening uh, in tectonic convergence zone between plates and are the result of both thermal and mechanical disturbance of the lithosphere. Not only the forces are important, but also the temperature. This doesn't work. Uh, the thermal perturbation is very important in making up an orogen. We have also the deformation and metamorphism of lithospheric rocks. We'll deal mainly with metamorphism and ductile deformation of rocks in this course, as well erosion and sedimentation. Erosion is very important, and also sedimentation. Uh, and also, an erosion can form an important climatic barrier, such as the Himalayas, that was built up after collision 55 million years ago, and it was a very big climatic barrier. And in the Himalayas, there was the first study by Jamaison and Beaumont, two Canadian geologists, that coupled the tectonic and climatic processes in the maybe in 2000, 2001, the first paper. They made a very nice numerical model of the orogen, including the erosion. Erosion was a very important factor helping tectonics to go on. Goes on. Mm. Okay. Okay. We deal with the collision, so we must recall Tuzo Wilson. He's a Canadian geologist that was the main developer of the Wilson cycle, but the Wilson cycle was named after this work by Kevin Burke in 1975. So, and Tuzo Wilson was famous for plate tectonics, also for the discovery of hotspot, transform fault, and the Wilson cycle that is a very important tectonic processes that will lead to the end to the formation of an orogen. At the beginning, you have a rift of the lithosphere, and the continent started to split by extensional tectonics. So you have a lot of normal fault in the thinned part of the orogen. After a lot of time, the continent are completely broken and separated, and the new oceanic crust started to develop in between. Then you have seafloor spreading, and after movement of plate tectonics, you can start subduction on one side of the two continents. Subduction means the, the oceanic crust go in subduction below the continent. You can have accretionary prism and some other things. After the total consumption of oceanic crust, you can have collision. So the two far continents come in contact one with the other, and with the formation of the continental crust. And during this process, you have erosion and sometimes the thinning of the crust, and the process start again. So there is a complete cycle that needs maybe 250 million years to complete. Mhm. And during the history of the Earth, there were several of these cycles leading to the formation of supercontinents, the big continents, the Pangea, Rodinia, and in the future, there are some tectonic geologists that are working with the GPS velocity of the continents, and in the next 250 million years, we will have the Pangea Ultima, a big supercontinent in the future, very far in the future. Okay, the process is very similar. In this paper, more recent by Wilson, but not the same Wilson, another one, of course. Uh, there is another picture uh, speaking of the Wilson cycle, but more or less the significance is the same. Okay. There is one difference at the beginning because you can see here not important subduction of the continental crust because during the development of plate tectonics, people believed that the continental crust cannot go in subduction because it is too light. Mm? The density is too small to go inside. But in the 80s, 1984, the French mineralogist Chopin, Christian Chopin, found coesite inside garnet in continental crust in the Alps, close to Turin, close to my town. And coesite means that the rocks underwent subduction up to 100 kilometers in the lithosphere. So after the 80s or the 90s, people believe that also continental crust can go in deep subduction. Okay. And in the same massif, the Dora Maira massif that we will speak about in the next lessons, we the people are finding a lot of coesite in oceanic unit, oceanic derived unit, in continental derived units, and in the last few months we found also fossils in ultra high pressure rocks. We found polynomorphs, pollen, and acritarchs of Silurian and Permian age inside the very high metamorphic rocks. So it was a very nice discovery just published 1 month ago in scientific reports by my research group. Okay, so uh, if we give a look to the convergent stage, bringing leading to the formation of the of a of an origin, you have the continent A, continent B. The continent A is affected by a passive margin, so a lot of extension. Now they are very common to find hyper-extended margins with a lot of piece of the continents above the oceanic crust and the mantle lithosphere exhumed by exhumation. You have the subduction of the oceanic lithosphere, the formation of a continental volcanic arc by the fusion of the continental oceanic crust, accretionary prism due to the convergence in between the continent B and the oceanic lithosphere. After that, you have the formation of the suture, because all the oceanic lithosphere is consumed by subduction. Sometimes oceanic lithosphere is transported above the continent by abduction. So you can have pieces of lithosphere not deformed or metamorphosed just above the continental crust. And at this stage, the continent collide, come into contact. In the Himalayas, the age of collision is around 55, 60 million years. There is discussion about this, but the most accepted age is this one. After collision, the, the game is not over. You can have the thickening. The lithosphere is thickened. There is erosion because the mountain belt is growing. So erosion is very active. And also exhumation of the metamorphic rocks, because the deep-seated metamorphic rocks are brought to the surface during the collision or after the collision. Mm. In this stage, you can have also uh, deformation towards the foreland. You can have two foreland, two fold and thrust belt on both sides of the origin, or on one side. It depends on the characteristics of the lithosphere. In the Himalayan origin, you have only a foreign basin in the south to the Indian side, but not to the Tibetan side. Okay, so this continent is uh, very strong for the Malian side. In this nice picture movie, we can see the movement of India towards the north, the collision, and the hyper-collision of the indentation tectonics proposed by Molnar in the 70s. And in this stage, India continued to push into Asia, and you have a lot of deformation in the continental crust, and also you can have a big transcurrent fault, strike-slip fault, such as the Altintag fault, and so on. You can see again, it's simple, but it is very nice. Subduction of the oceanic lithosphere, collision, and the formation of the main thrust of the Himalayan belt. Main central thrust, main boundary thrust, main frontal thrust that you know very well because you live in this. Okay. Uh, about climatic and tectonic processes up to 1000, people don't believe that erosion was important in building up the origin, but after this paper, there was most important by Beaumont and others, 2001. They proposed a channel flow model that we will speak about in the next lessons. Uh, and this channel flow model mm, deal with molten rocks below Tibet flowing to the south, and this process is allowed by the monsoon erosion because the monsoon is active since 25 or 30 million years. So in this long time, the amount of erosion is comparable to the amount of convergence and tectonic velocities. So it is very important process to develop tectonics. Okay, and this is the first paper that pointed out to this aspect. So erosion is very important. Now it is not the fundamental factor, but erosion could help tectonic to proceed. Okay, in this picture you can see the Himalayan from satellite. You can see Mount Everest here to the south and the very dry region of Tibet. So you have a lot of erosion of the southern flank of the belt. Uh, Erosion, putting away some sediments, the most part goes into in the Bengal Fen, okay? This is dry Tibet, and this is Nepal, who is green aspect. Okay, the erosion at the mountain front is very different because you can see the rainfall millimeter for years from India, Nepal, and Bhutan. In Bhutan, you reach more or less 5 meters and a 50 centimeter of rain in 1 year. Is a picture of one expedition in Bhutan where we had a lot of rain during the day and the night for 20 days. So very few work, few sample collection, and we had to do it under the rain. Okay, just to remember the geometry of the mountain building, you have the internal zone of hinterland where metamorphic rocks are present. Much metamorphism happened in this rock. You have a fold and thrust belt moving the belt towards the foreign basin. You have the foreign basin filled by sediments coming from the eroded mountains and the continental interior with no deformation. It's just to remember the main characteristics. Okay, if we give a look to the world, this nice picture, not so precise, but just to have an idea what happened of what we have in the world. In orange, we have the shield, the platforms in violet, orogens in green, blue, this one. We have the active orogens or all the orogens, the basins in this color, large igneous province in this color, such as the cantraps that you know very well, and the extended crust in yellow. So just to have an idea of what happens at the world scale. Mm. In the same picture, similar picture, you can see the different periods of activity of orogen. Starting from the Archean, you can see in the South America, North America, on Australia, Siberia, China, the most ancient crust, early Proterozoic, Greek, middle Proterozoic, late Proterozoic in violet, Paleozoic in blue, more or less, and the Meso and Cenozoic in yellow. So you can see different ages of formation of orogens all over the world, just to have a broad idea. This is not so precise because the Variscan orogen, the Paleozoic orogen, is lacking in this part of Europe, but just to have an idea of what happens in the world. Okay, we'll speak about the Himalayan belt that you know. In Europe, with the relief map, you can see the Alps, the chain of the Alps. Turin is just here. Mm. The Apennines, and this part is made by Paleozoic rocks, the Variscan orogen, cropping out in all this part, this island, and also in some part of the Alps and the Apennines. Mm. So just to have an idea of the geography. Okay, I put some names because they're not so familiar. Yeah. Okay. The origin can be classified as a linear origin, such as the Urals, in between Europe and Asia. Is the green belt formed during the lower Paleozoic. There is only curvature in the northern part of the polar Urals, and these are very long and very linear. This is 500 kilometers, so you can see the very long development of this orogen. There are some orogen, such as the Variscan orogen in Europe, that is made by a carved shape. You can see more or less the main attitude of the tectonic contacts of the fault in the Ibero-Armorican Alps. Ibero means Spain. Armorican is this place of the French nation. And there is this curvature and another one in the east. And this part is affected by the very huge shear zone that we will mm, deal in the next lessons. Okay. Apart from the shape, there is an older former classification of origin by Hank Zwart in the 70s, because he divided alpine type origin, such as the Himalaya and the Alps, and the Hercynian type, or Variscan type, based on the structural, metamorphic, and magmatic characteristics. But Hercynian or Variscan type orogen, the Paleozoic one, are characterized by a large volume of granitoids and regional high temperature metamorphism and poorly developed fold and thrust belt. Okay. In the alpine type orogen, we have metamorphism. It is high pressure or ultra high pressure metamorphism, few granitoids, and a well-developed fold and thrust belt. But these differences are not real. because it depends on the history of the belts. So at the end, after the development of plate tectonics, we that the origin are made by the same processes. So it depends on the amount of thermal energy and the tectonics involved in the processes. You have the same history. Okay, so there is not a big difference characterized by this. So a much more modern classification of the origin is made by the one proposed by Beaumont and others in 2006. That is similar by the classification of the star in the Hertzsprung-Russell diagram. You have here the temperature and here the luminosity. And for the origin, you can have here the temperature, more or less the same. And instead of luminosity, you have a magnitude of the origin, so the amount of lithosphere involved in the process. And the classification has two end members. You have a large hot origin in this part of the diagram, and here the mold called origin. And for example, you have a main sequence, such as the star. So a small called origin can evolve towards a large hot origin, and you can see some kind of origin. The Southern Alps in New Zealand is a classical, very small cold origin. The Alps are here. The Greenvillian Canadian in the Canada is here. The Variscan is this side, and the Malayan Tibet is the most classical example of large hot origin, because you have a large lithosphere involved in the process and a large amount of granites, and the high temperature is testified also by partial melt crust. You have a lot of migmatites inside the origin involved. Okay, this is more or less the same sequence. So you can have also a trend like this, and you can deviate from the orogenic main sequence towards another kind of sequence, like the one followed the Variscan origin. Okay? So the processes are the same. It depends on the temperature, on the amount of temperature, and the amount of lithosphere involved. But the tectonic processes are more or less the same. Okay, so according to most of the author, Himalayan Tibet is a classical large hot origin. The crust is 68 kilometers thick. There is a central elevated plateau, the Tibetan plateau, nearly 5 kilometers, flanked by wedges and foreland basins. There is a mechanically strong upper crust, superstructure, very weak infrastructure. Ductile flow of the weak infrastructure is in response to pressure gradient. So these are the main feature, and you can see a picture from the Tibetan side to the Mount Everest from the base camp in Tibet. And this is from the Tibetan side, just Mount Everest and maybe Cho-Oyu. So you can see the snow level at the 6,000 meters. Okay. Another classification of the origin is made by Carlo Doglioni. Do you know the symmetric art classification? Or Carlo Doglioni is a professor at University of Rome La Sapienza. This one just a few days ago during the conference, and he proposed that the Earth is asymmetric, because you can have some very steep subduction and very shallow subduction, and it depends if the subduction is towards the west or towards the east, because there is a flow of the asthenosphere from west to east. If you have a subduction that is opposite to the flow, the subduction is very steep, and the the chain above has some characteristics. If the subduction is in the direction of the flow, the mountain belt above is of alpine type with different characteristics with respect to the Penninic types. This is below, so west dipping subduction and east northeast dipping subduction are very different and give rise to different characteristics. Uh, the the continent move according to equator, a tectonic equator that is not the geographic one, but shows a sinusoidal shape. So the continent flow this direction. So in the Himalayas, you have a northeast dipping subduction, the subduction of the Indian plate below Asia, and this flow of the asthenosphere to the east is caused by difference in density between the lithosphere and the mantle, because lithosphere is less dense than the mantles, and during the rotation of the Earth, lithosphere move in this direction. So the velocity is less than the velocity of the mantle. So you have this movement, and then there is a flow of the asthenosphere to the west. The main cause uh, of this flow. And according to Doglioni, uh, the mountain belt are asymmetric because if you have a west dipping subduction uh, uh, in opposite direction to the flow of the asthenosphere, you have an origin that is smaller with respect to the origin that build up above subduction in the direction of the flow in the asthenosphere. So more or less, he studied the Alps. It is this kind of belt, and the Apennines, this kind of belt, and he expanded this study to all over the world. You can see here more or less the main feature of the Alps here, the Apennines. You can see here the steep subduction below the Apennines with the volcanic Alps, the Eolian Islands, and a very deep earthquake up to 500, 6,600 meters below the Ionian Sea, whereas the Alps go in this direction in a very shallow angle with respect to the African crust, just to have an idea. Okay, so the two different type are this one. Apennine to the right and the Alps to the left. Okay, the main feature are these. The change is double in the Alp. You have divergence towards the plane and towards the European side. The angle of subduction is one angle of subduction in the Apennine. So you have one single vergence that is towards the east in the Apennines, towards the Adriatic Sea. The topography is high in the Alps. You have several mountains reaching 4,000, 4,500 meters. And whereas in the Apennines is very low, the maximum altitude is 2,000 meters or 2,500 and so on. You have no back-arc basin in the Alps and a well-developed back-arc basin in the Apennines. The foredeep basin, you have two shallow basin with low subsidence in the Alps, and in the Apennines, one deep basin with rapid subsidence. About metamorphism, the basement is deeply involved in the alpine orogeny with large volumes of exposed high pressure, low temperature metamorphic rocks. In the Apennines, the basement is less involved, small volumes of exposed high pressure, low temperature rock. Okay. The magmatism related subduction show less volume of the alpine chain and much more voluminous in the Apennines. So you can extend this classification all over the world. And so the difference that Hank Zwart found in the 60s were caused by these different subduction direction. So there are some difference, but not in the processes, but in the subduction direction. Okay. You can see here also the actual altitude of the Apennines and the estimated amount of sediments of rocks eroded up to 3,000 meters. 2,000 meters. In the Alps, you have much more developed topography and much more amount of rocks eroded in the Alps. Okay. From Carminati and Doglioni, Earth Science Review. There are many, many papers about these topics. Okay. So you can see here the Pennines with the Becar here. It is the Iranian Sea. Whereas in the Alps there is no Becar basin. Okay. Yes. They're more or less the same things, but I left some more picture on the right in the slides. So when you have a PDF, you can read. Okay, the Europe. Okay, this is a picture, and this is a uh, aerial view of the Europe. Mm. And in the geological simplified geological map, you can see Cenozoic alpine belt. That means the Apennines, the Alps, uh, Denariad orogen, and so on. In orange, you can see the rocks deformed in the Variscan belt during the late Paleozoic, the lower Carboniferous. And you can see that the most part of these rocks are not affected by later orogen, whereas in the Alps and the Apennines, you have pieces of orange rocks inside. That means that these all the rocks are involved again in new orogens. So it makes a little bit complicated the reconstruction inside this belt. In the northern part of Europe, you can see also the Caledonian orogen developed during the lower Paleozoic. So you have a lot of deformation, and of course, the study of the Malay of the Alpine belt and Apennine is quite easy, not very easy, but uh, possible. Whereas the study of the Variscan belt is much more tricky because several pieces are displaced, reworked in later orogens. Also for Corsica and Sardinia, Corsica and Sardinia was connected to French Spain to 25 million years. Then they rotated during the Apennine origin. So the Calabrian arc, this side, was put in this position, then in this, then migrated away towards the southeast during the opening of the Ionian Sea and the Bekarka Basin in the Apennines. So the the construction is Variscan belt is a little bit tricky. Okay, we will speak about mainly of the Variscan origin in Sardinia and Corsica Islands. that a beautiful island in the Mediterranean Sea, and they are not affected by later origin. So you can see the structure as they formed in the late Paleozoic. Okay, about about the ocean crust involved in the Variscan Belt, there are several hypotheses, or one oceanic crust, two oceanic crust, three, four, five, because up to the 19, also 2000 years, some people found alignment of Ecolgite rocks, and when they found a large amount of Ecolgite, they put an ocean. So in the literature, there are several oceans separating the Variscan, small pieces of the continent involved in the Variscan belt. Up to now, after this paper by Ferrier 2022 in Geosciences, uh, the suture and the oceanic crust involved is only in three places. Le Conquête suture in this part, the Eovariscan suture here, and the Tepla suture here. So there are the three recognized suture zone with involvement of three small or big oceans, separating fragments of continents involved in the collision of the formation of a Variscan belt. You can see here Corsica and Sardinia that are now in this position, but at the Paleozoic they were in this position, close to France, and also the pieces of the Variscan rocks in the Alps that are now deformed in a curved way, they were aligned in this position, just to have an idea. Okay, this is the same concept. In violet Paleozoic rocks affected by Variscan orogeny. And you can see here Variscan orogeny involved in the Alpine orogeny. If you remember a few slides ago, Belloni stated that much more basement is involved in Alpine type subduction and less basement is involved in the Apennines. There are only few pieces in Tuscany and so on. So just to have an idea, this Pyrenean orogeny, that is the formation in this side. Okay, but for example, if you go in Spain, Massif Central, in Brittany, you can see the rocks as they were deformed at the end of the Carboniferous. And just to have an idea of the continent during the early Paleozoic, you can see Gondwana to the south, this ocean called the Lake Ocean, the Armorica Barrandia continental crust from the Armorican in France, the Lake Ocean, that was quite big, the Avalonia continent. Then you have Japetus Ocean with two arms, a Tornquist, the Japetus continent, separating the Laurentia to the west and Baltica to the east. So the Caledonian origin was formed by the collision of Baltica and Laurentia. The North Japetus was closed with the suture, and you can find this origin in Norway, Sweden, Denmark, in the northern part of Italy. This happened in the lower Paleozoic. After that, Gondwana started to move to the north, and Laurentia and Baltica, called Laurussia, started to move to the south, and you had the closure of the this ocean, the Rake Ocean, and the Take Ocean. So you have more or less two suture in this zone, leading to the formation of the Pangea at the end of the Paleozoic. Okay, Have you some question about this overall picture? Yes. Yes, there's a stripe shaped continent. It's not so big, but very long. Mm. Okay. Okay. And this part is ended. Mm. We can okay, 10 minutes before we can start the second part. Okay. Mhm. Mm. Okay. Sorry. Mm. All the cold, all the hot. Yeah. Yes. Yeah, usually all the halogens are hot, but also the Himalayan Tibet halogen is very hot. Yeah, because you have a lot of migmatites below Tibet, where seismic profile showing the hot melt below Tibet. So the amount of you have also a lot of migmatite cropping out in the Greater Himalayan sequence with a lot of leucogranites of Miocene age. So very, yeah, welcome. So now we will give some information about the deformation of the rocks. Go into a little bit into depth of this kind of feature. We will speak about briefly of elastic deformation, elastic brittle deformation, fracturing, granular flow, cataclastic flow, with example for natural faults and fault rocks, friction and its control on rock strength in the brittle upper crust, and rock deformation experiments. But just a brief information. After that, we will start to speak about shear zone in the crust on the lithosphere and the kinematic indicators with some practical exercise in the afternoon. The books are the same, of course. Okay, you can see in these two pictures two different kind of deformation of the rocks. This is the San Andreas fault. This is a brittle fault cross-cutting the lithosphere, as you know very well, generating earthquakes. Mm. And on the left, you can see a folded calcite vein in the northern Apennines. So this a classical ductile deformation or ductile structure. You can deform the rocks without fracturing, and this is a deformation by fracturing, losing cohesion of the rock. So this deformation are due to the application of forces to rocks, and usually a small amount of deformation is due to elastic deformation that is recoverable. You can deform a little bit. If you do not apply the force, the rocks come back to the original position with no permanent deformation. But this is a small amount of deformation in the rocks. Uh, in structural geology, it is very important the stress, that is the force divided the area, because the deformation it is not the same if you apply 1 kilos to 1 centimeter square or 1 meter square. So the amount of force is is important, but the area on which it is applied, it is causes deformation or not. So deformation usually involve a change in the position of the rocks, movement of the whole body, a change in the shape. You can see this thin section with oolitic limestone. When I apply deformation, there is a change of position, but also a change of the shape. From circular object, they become elliptical. This is a very clear example of change in shape. Sometimes you can have a change in the volume of the rocks. For example, when the sediments uh, became rocks, you decrease in density, you have the expulsion of water, and so on. So usually you have a decrease in volume of this, of the sediments becoming rocks. Okay. The classical example of elastic deformation is the rubber. When stretched, it returns to its original shape once the force is removed. And each rocks have its own elastic limit. Mm. After that, you can have a permanent deformation that could be brittle or ductile. But the behavior of the rock depends of the elastic limit. That it depends on the temperature and on the pressure that controls the mechanical behavior of the rock. And usually in a stable continental crust, you have the pressure that increases with depth at a rate of 33 megapascal for kilometers due to the lithostatic load of the rock, mm, the weight of the rocks. The temperature increases normally with a rate of 25 centigrade Celsius centigrade for kilometers, and the temperature promotes plastic deformation of the rock. Of course, if you are in a subduction zone, the gradient is much different, maybe 18, 15 degrees per kilometers. If you are in a geothermal area, such as in Tuscany, you have the mantle just 3 kilometers below the surface, so the gradient could be 50 kilometers per kilometer. So I refer to a stable continent with no much deformation. So if we give a look to the rocks in a vertical crust, you can see different behavior deformation due to the increase of pressure and temperature going down, of course. Other factors that affect the deformation of rocks are the presence of fluids. The fluids are very important for metamorphism, for metamorphic growth and metamorphic change of minerals. And the fluids also favors brittle deformation. If you have high pressure fluids, you can break the rocks even they are in the depth. Mm. And also the deformation rate is very important because low deformation favors ductile behavior, so folding and shearing of the rocks, whereas very short deformation favors the fracturing of the rocks. You can see this example in the pack of Antarctica. Pack is the seawater, uh, the ice made by seawater. You can see here a glacier flowing from the higher part of the Antarctica towards the sea. You can see the flow lines and the folds because the flow is a few meters a day. And in this case, the pack that is thick 2 meters is broken by the strong wind flowing from the higher part of the um, of the continent, the katabatic wind that reaches 200 or 300 kilometers uh, per hour, the velocity, and in this way very fast deformation broke the ice into pieces. The same is the rocks. Slow deformation favors ductile deformation. Very fast deformation allows the fracturing of the rocks. Okay. In this classical experiment, as reported in the book by Twiss and Moore in 1992, uh, a piece of marble is made by limestone recrystallized the static growth of minerals. This marble is subject to deformation under different pressure: 0.1 megapascal, 3.5 megapascal, 35 megapascal, 100 megapascal. You can see in this case there is a longitudinal splitting, the sigma 1, the main stress in this direction, and the pressure parallel to the sigma 1. Increasing the pressure, it means going a little bit down in the crust, you can see a single oblique fracture, and at at, 35 megapascal, you can see the transition in between brittle and ductile. You can observe something like fracture, conjugate fracture, but also the shape of the rocks change. It is a little bit compressed in vertical and extended in horizontal. Whereas at 100 megapascal, the deformation is completely ductile. So the body change the shape, is shortened in vertical and lengthened in horizontal with no fracture inside. So, okay, with you can see the different, this uniaxial deformation, triaxial depends on the condition of the experiment, but okay, just you can see in this picture by Fossen, in the book of Fossen, you can see sigma 1 with one fracture, sigma 1 and sigma 3, the confining pressure uh, develop one single fracture. The brittle ductile transition is one of brittle deformation, but a little bit wider, and the changing in the body due to sigma 1 and sigma 3, and the completely ductile deformation. In this diagram, there's a strain, elongation, and the stress. There is an elastic portion of deformation. After that, after the elastic limit, the rock underwent rupture and fracture. The same here. You can see the different shape of the red curves. The elastic, brittle deformation, elastic, brittle ductile deformation, and elastic and plastic deformation. So different. We will come back here in this graph later. Mm. Okay. Here's a nice picture by Fossen. You can see a fault cross-cutting of the lithosphere with morphological expression at the surface. You can see the fault here. The first 10 kilometers, you have fault with cataclysmic rocks, incohesive fault rocks in the first kilometers, and the cohesive fault rocks towards the depth. At 10, 15 kilometers, there is a transition between brittle and plastic deformation because I remember you that the temperature and pressure are increasing. So, but of course, the transition is not sharp, but in a stable crust, it occupies nearly 5 kilometers. So the behavior in brittle and ductile, the transition happens in these 5 kilometers. Below 15 kilometers, you have ductile deformation. So the fault became a shear zone. The deformation is wider and wider, going into depth. And in this case, deformation is is happening during metamorphism because you have grenache facies, amphibolite, granulite, colgate facies going to depth. So deformation and metamorphism goes together, mm, are not separated. Okay, this is a picture from Ray and Mataware, where you can see the same deformation but in a contractional setting with folds and foliations. In the upper part, the deformation is brittle, the crust is brittle, and then you have a fracture and folds. You are in the upper structural level, so you are in this part. You can have also some folds, but they are passive folds or folds linked to thrust or to the geometry of the folds. In the transition zone, there is the brittle ductile transition. So you can start to form folds with a foliation of axial plane foliation in folds. Below 15 kilometers, there is completely plastic deformation. You have pervasive deformation, pervasive foliation. So the foliation is dominant in all the rocks deformed. You have folds, ductile shear zone, and also recumbent fold, tectonic transposition. So the original stratigraphy of the rocks is almost completely concealed or transposed by tectonic processes. Uh, Pervasive surfaces, defoliation, and polyphase deformation is very common. And you have ductile shear zone with myelonites, the fault rocks. And at the end, when you reach 650, 70, 700 degrees, you can have also the formation of pegmatites because you are close to the boundary of melting of the crustal rocks. Uh, okay. Okay, come back to elastic deformation. This classical example of elastic deformation, as probably you know, is a spring. You apply a force to a spring, the spring change in length. After releasing the force, the spring return in the initial state, so deformation is completely recoverable. In the rocks, this is nearly 1% of deformation, no more. 1% is this kind of elastic deformation. You know that the relation between the stress and strain is E, the Young modulus, just to remember. The relation between deformation, strain, and stress is linear. Classical example, very, very easy. In this graph, you can see uh, linear elastic during extension or contraction is the same symmetric situation. And just to have an idea, the Young elasticity modules in a gigapascal for quartzite, gneiss, granite, limestone. We can see that quartzite is a more uh, strong rock in respect to gneiss, basalt, granite. The shale of quartz coal are the less strong rock. Okay. This is very nice example because you have a rubber band in equal state. You can load by, by this quartz, the material change in length, and after that, the elastic limit is overcome, and there is a fracture just here, but the fracture is confined in this position. The rest of the body maintain the original structure with no damage or faults or fractures. Okay, Coming back to the crust, the brittle deformation in this part of the rock is made by fracturing or frictional sliding. Uh, the brittle the brittle flow that is in the lower part of the brittle field is made of a granular flow that is frictional sliding or rolling of fragments, and the cataclastic flow that is made by grain fracturing. This means that you have a flow made by a rotation movement of grains with no fractures, but the cataclastic flow is made by fracturing of grain, and they develop a flow in a brittle condition. Just in this part, in this picture, you can see a brittle rock deformed. So these are cataclysite, this intact rock, and these are cataclysite made by fragments of the regional rocks. And here you have a cataclastic flow made by the fracture of grains moving in this part, allowing the deformation along this fault. Is an outcrop of Norway Caledonian origin. Okay, just the same things. Okay, in the brittle regime, there is the formation is governed by the Bayerly law. Someone of you remember the Bayerly law? This never. Oh, it is a linear correlation stress and strain in the first maybe 10 kilometers of the crust. So means that the deformation is the same in all kind of the rocks, independently of the it is a quartzite or granite, but the slope of the line is 0.85 maybe. Means that the relation is the same. So in all the rocks of the brittle part, you can follow a line like this, more or less. Not a good exposition, but explanation. But it is very, very common. Okay. Okay. So when you have a rock and the you have the flow. So no, you in the brittle ductile portion on the ductile portion of the crust, the force with the rock made the flow. The flow means deformation that could be by faults or by shear zone, ductile portion. Okay, and the rheology is the study of the flow and deformation of all form of the metal. And during the flow, the deformation is controlled by the viscosity of the material. Mm. So we are going down, and the plastic deformation, the classical model is blocked on the surface. You apply force, you have to overcome attritus in the surface, then the block starts to move. So this is in the graph, you have velocity of deformation and the stress applied. Nothing happen, you increase the stress, you apply the force. Nothing happens until you reach the yield stress. After that, you overcome the attritus of the surface, and the block start to move at the constant velocity. And this is the perfect plastic deformation. Plastic means deformation of rock, not a molten rock. Okay, this very ideal deformation, perfect plastic, and it could explain some kind of deformation of the rocks. The viscous deformation is the other way of deformation, but is much more applied to fluids. such as migmatites, for example, are useful for plastic deformation. Uh, you have a piston with oil inside, with separation. You applied the force, but the linear viscous deformation in this graph by velocity of deformation and the stress applied, the relation is linear with no yield stress like plastic deformation. But when you start to apply the force, uh, the movement the piston start to move in a linear way. And this deformation and also a plastic deformation are not recoverable. So the permanent deformation. So you can start to deform the rock and the deformation maintain its deformation. The fold are forever. Okay. And the viscosity with this strain symbol named eta by Greek alphabet describes the way in which fluids flow. So this the tangent of this angle eta is the viscosity of the material, and of course different materials have different viscosity. This is a difference, just an example. You can have a plastic material, nothing happen. If you load, if you apply force, the plastic material start to deform. Removing the force, the deformation remain. Maybe some piece of this one. In the viscous analog, you can put the spherical plastic material that start to deform under gravity force, and deformation is permanent in the same way, but without a limit, a yield strength. Okay. For real rocks to deform, you can see a beautiful shear zone in Canada with a porphyroclast rotated, a very big one. Uh, you can see that for the rocks, the deformation is could be represented by this graph with a small part elastic deformation, then a plastic deformation, but not perfectly plastic because this line is not parallel to the to this coordinate axis, but increase a little bit. This means that after reaching the yield stress, you need to apply much more stress to make the rock to flow, to move. Okay, not in the classical perfect plastic deformation. At this point, you have this behavior with the same force, you can maintain the same rate of deformation. In the real rocks, you have to increase stress to allow deformation to go ahead. And this behavior is called also strain hardening. Okay. Instead, if there are some facilities of deformation, easy rocks to deform, such as gypsum or fluid in the rocks, you can have a behavior with a line in this way. So you have to decrease the stress to maintain deformation, and this is called strain softening. Okay? So this just to have an idea of the viscosity of the fluids. Water, honey, basaltic magma, spirited magma, mantle rocks with olivine, and the crustal shear zone. You can see, for example, crustal shear zone has a viscosity uh, Pascal per second, 10 to 15, 10 to 19. So very, very high viscosity of the rocks, comparable or a little bit lesser than mantle rocks, much more than silicate rhyolitic melt, and much more than basaltic magma. Just to have an idea, because we have usually uh, information like this. Okay. So we go towards the shear zone a little bit. So shear zone and faults. Shear zone are ductile structure, fault are brittle structure, but uh, but they show strain localization. So deformation is localized in a very thin sector of the lithosphere, brittle if you have faults, and ductile if you have shear zone. Shear zone is characterized by continuous ductile deformation. So you have a displacement of these two blocks with no loss of continuity and no fracturing in between. Whereas brittle deformation is discontinuous. You have a fracturing here, loss of cohesion, and you have the same displacement but with much more localized deformation along a fracture of a damaged zone characterized by cataclysite, tectonic breccia, and so on. Whereas in shear zone, the deformation is continuous. Mm. You can see here a brittle deformation uh, deforming these rocks with this dike. Okay. Okay, this graph used by Fossen, you can see here brittle deformation, plasticity as deformation mechanism, and plastic deformation, because the plastic is the terms related to the rheology of the materials, whereas ductile is related to the structure. It's not the same. Right? So you can put brittle, plastic material, non-ductile, and ductile. You can see here the folds, semi-ductile shear zone or brittle ductile transition, and the shear zone, ductile shear zone. Just another way to see the same things. Okay, here an example of geological structure. Do you know what is this? Some of you tension gases? Yes. Is a typical brittle ductile transition because you have fracture uh, like this filled by material, maybe calcite or quartz, but the deformation is not along a plane, but is in a wider part of the rock. Some of you can say the sense of shear. What is the sense of shear in the tension gases? Up to the right, in this way. Yes, yes. And these are fractures that start in this position because more or less you have a sigma 1 like this. So you have the maximum compression, maximum extension, and after moving, the fracture rotate towards the right, and the new fracture forms in the good position with respect to the sigma. So you have this sigmoidal shape. And what is the picture on the right? There's maybe shear zone, but because maybe this is a granite from the Alps where Menegone and Pennacchione studied, good morning, studied a lot of shear zone because there is a very nice place left free by glaciers that are melting and melting. So up to 20, 30 years ago, this area was covered by glaciers. Now it is completely exposed and very clean. And you can see this granite undeformed, here undeformed. And you can see here localization of the formation. You can see isotropic rock, and you can start to develop the foliation like this. And then there is an intense development of melanolitic foliation inside the shear zone. So this is a completely ductile deformation. You can assess the sense of shear of this picture, in this picture. Try. Hmm. Top right. It is top right because you can see this foliation going in this in this position and this in the opposite part. So the movement is like this. Okay. We will go in depth in kinematic indicators in this afternoon. Okay, to try to be sure of the kinematic indicators. Okay, this is just terrorism, but I will not go in in detail of this because of the laws that rheological laws that affect ductile deformation are expressed in this way. This is the velocity of deformation with several kind of terms, exponential law. So these are not single lines, but curves in the diagrams. And this explain the behavior of the rocks, but just uh, so you have not a question like this, but is more or less exponential law is the exponent that could be 2, 3, 4. 2 it's okay, 3 it's okay, but 4 is very complicated. And deformation, just to have an idea, is related to stress, the stress exponent, that is very important. The grain size of the rock is very important and it is related to stress and strain. The grain size exponent, the temperature, activation energy, and the universal gas constant. So it is a little bit complex, but could explain the ductile behavior in the ductile part of the crust. Just to have, just to recall this. Okay, and the for exponent n1 are viscous materials, so-called Newtonian materials, that is much more easy to deal with. And if n is larger than 1, you have a power low materials. So n could be 2, 3, and are a little bit more difficult to explain. And this kind of law regulates the behavior of the rock in the ductile deformation, where you have plastic flow by diffusion or crystal plasticity. We go into depth of the formation mechanism tomorrow. So to understand the deformation mechanism in this part of the lithosphere, we need to look at the crystal lattice of minerals, how mineral deforms, how rocks deforms, are regulated by deformation mechanism, and we can recognize this deformation mechanism under the microscope. It is quite easy to recognize different kind of deformation due to different lattice deformation of the crystal, but we need not to go at the transmission electron microprobe or electronic microprobe, but just to look at the microstructure of the quartz, of the feldspar, of the calcite, we can infer the formation mechanism in the ductile deformed rock. And we will deal with these things in the next, maybe tomorrow. Okay. Okay. Have you some question about this part? Okay. Crystal plasticity means the formation inside the crystal by the movement of defects in the crystal, maybe point defect, linear defect, or planar defect. And diffusion is the movement of atoms at the surface of the crystal. So a little bit different. We will explain tomorrow. Thank you for the question. Okay. So we can go ahead with the shear zone. Okay, so we go into depth in ductile deformation by deformation in shear zone. I avoid folds and foliation. Foliation we will deal with in the next lesson, but the folds I assume that you are trained on the folds and a little bit lesser on the shear zone. So in this part, we will define what is a shear zone, what is a deformation within a shear zone, evolution of the fabric in a shear zone, different types or kinds of shear zone, and what are myelonites and how we can recognize. Okay, so we are in this part. mm, Deformation characterized by ductile structure. You can see the shape, this shape is due to the power law deformation with the exponent maybe n equal to 2 or more or less. And in this kind of, mm, of crust, you can find ductile, completely ductile shear zone. So ductile shear zone are long and narrow zones of relative displacement. They are the same analogous to fault, but without fracture planes, unless they are reworked, because in nature you can have several superposed deformation. So you can have a shear zone, then fractured, or fractal, then shear zone. So, but a single shear zone usually has no plane of fracture uh, because dominantly ductile deformation has caused the concentration of large strain into the shear zone. So it is a concentration of deformation and shear in a narrow and very long zone. Deformation in the ductile shear zone is associated with a drastic reduction of the grain size and development of well banded and lineated rock called myelonite. Ductile shear zone records non-coaxial deformation. So there is a deformation characterized by both simple shear and pure shear, because the simple shear and pure shear are end members of deformation, but in nature you can have usually the combination of these two factors in a shear zone. And shear zone may range from the grain scale or microscopic scale to the scale of hundred of or thousand of kilometers in length and a few kilometers in width. So the scale is not a problem. Uh, in the Himalayas, there are, of course, a very huge shear zone. The main central thrust run all over the Himalayas for 2,000 kilometers. The same as the South Tibetan detachment in the upper part of the Himalayas has 2,000 kilometers in length, and the width maybe up to 1 kilometer. So the main central thrust is up to 4 or 5 kilometers. So the scale, and also the displacement could be few centimeters up to maybe 2,000 kilometers for the main central thrust or other important shear zone. Okay, the localization of the formation in the shear zone reflects the continuous but heterogeneous strain in the rock. Okay. So, according to the initial definition of Ramsey-Huber, shear zones are defined as planar or curviplanar zone of a deformation to have a length much greater than their thickness and surrounded by rocks characterized by significant lower deformation. This is a shear zone from the Adamello granitoids in Italy. This is non-deformed. This is a shear zone with a strong deformation, and this is undeformed. And there is also a spatial gradient of deformation. Cioè in the space you can observe a gradient, an increasing deformation from this part towards the center of the zone, and then deformation decreases towards this part towards zero deformation. Mm. This is just an example of a granite before deformation. You can see quartz, plagioclase, tight, diciamo, with no deformation, isotropic fabric that could be represented by a circle. And then after deformation, after simple shear, you can see here the circle became elliptic. You can see that the minerals are deformed, are aligned in this position, are stretched in this way, and compressed in this way. So the shear zone causes a deformation of the granite of this granite in a shear zone. Mm. We are in the Variscan shear zone in the island of Corsica, which is politically belonging to France, but once was belonging to Italy to some centuries ago. And you can see the wall rock here, and then a big shear zone. But you can see that here there is a foliation. There is an older foliation with respect to a shear zone. So you have a regional foliation acquired during Variscan collision, then a shear zone affecting this Variscan collision with a new deformation concentrated in this part of, of the shear zone. So in the ideal case, like this, the wall rocks is completely undeformed because you have here only the granite crystallization and the shear zone. But in the mountain belt, you observe usually several kind of deformation superposed. So the regional one, this one, and the shear zone. And you can observe a thickness of the shear zone that more or less half a meter. Uh, Grain size reduction. You can see these are more or less feldspar crystal that are very little bigger here and very small here. The white point in the myelinite. So deformation during the shear is concentrated in this part. And you can see also the older foliation that is folded by the shear zone in this way. Okay. Here we can see in this nice experiment by gypsum. Gypsum is undeformed. You can see the crystal under the microscope. Isotropic crystal with no deformation or so nothing of strain. You applied a shear stress. You can see the shear stress here, gamma, that is the tangent of this angle, the gamma, for the simple shear. And the deformation was at room temperature. You can start to move the upper part to the left, and you can see the gamma is more or less 1, so the angle is 45 degrees. Mm. And just with gamma 1, you can see that this crystal, that are more or less rounded, became stretched and aligned in this direction. And also the color is different. You can see here green, blue, red. In this part, the color of the crystal are the same. That means that the crystallographic orientation is the same. This the crystallographic orientation is in different position. This is concentrated, aligned in one position, and this is very nice. You can see the development of the shear zone until the breaking of the sample, because of course it is a few centimeters, so it is not possible to have a big deformation. But you can see uh, strong localization deformation with strong crystallographic orientation of the minerals. This is gypsum, but the same happens from quartz, calcite, olivine, lawsonite, depend on the metamorphic grade of the shear zone. You can see again, if you look also to the gamma increasing, so means that the angle of shear is increasing, giving to the left sense of shear. Okay. In this graph by Jean-Pierre Bourg, that was professor of structural geology at the ATH in Zurich, Polytechnical Federal Institute of Zurich. Jean-Pierre Bourg is very famous in Himalaya because he discovered the South Tibetan detachment in 1983, because at that time it was considered a trust by Chinese geology, but he studied the leucogranites deformed along the South Tibetan detachment, by studying kinematic indicators such as like a microfiche as structure, he recognized a uh, normal shear zone, normal sense shear zone. It was a very nice discovery, because at that time all the people believed that mountain belt are made by compressional tectonics. It means folds and thrust, but no shear zone or extensional shear zone or extensional fault. But after 1983, people started to think about both contractional and extensional shear zone at the top of the origin, and some models were developed. For example, the John Platt model is compression at the base and extension at the top. So different model start to be involved in the mountain belt. But the starting point was Jean-Pierre Bourg working as a for the PhD thesis in Tibet. Stayed maybe 2 or 3 months in Tibet looking at the deformed rocks. And by recognized kinematic indicators, we gave the right interpretation of this huge shear zone. Okay, so coming back to this graph, you have here deformation, axial deformation. Axial load means stress. You can see the red line, the classical shape of deformation, very general shape, linear, uh, and plastic with strain hardening. But usually you have recoverable deformation up to this point, then homogeneous deformation. Then there is a possible bifurcation of deformation in every stage. You can continue to deform the rocks by homogeneous deformation, or you can localize deformation along shear zone. So the meaning is very general for this. But at any stage of deformation, you can start to localize deformation, maybe for the presence of fluids or crystal oriented in a particular way, allowing deformation to flow in a particular direction. So in this way, you can deform the lithosphere and make a lot of displacement along the shear zone. So, so you need to localize the deformation from homogeneous deformation to localized deformation. Okay, this shear zone from the Jotun Napp in Norway, Caledonites, and you have a shear zone with malonite is enriched in epidot, because there is maybe a decrease in deformation and the presence of fluid, allowing the crystallization of epidot inside the highly deformed area. And you can see all the characteristics of the shear zone: localization, less deformed wall rock below, above, grain size reduction. You can see big crystal, maybe feldspar here, and the small feldspar here. That amount of foliation, fine grained defoliation here, and an extra sense of shear is detected by the defoliation attitude. This is a very good example. This is another example from Pennacchione in Adamello, the same feature. So this foliation is growing during the formation of the shear zone, because no foliation outside, but foliation inside the shear zone. About the scale, is a nice paper, a review paper for the shear zone by Hakun Fossen and Carolina Cavalcante in 2017 in Earth Science Review. This is a nice paper I suggest you to have in your library. And this is a shear zone at a microscopic scale with displacement more or less 1 centimeter. And this is a shear zone in the Canadian of the Creton, no, Canadian Creton, with displacement of several hundreds kilometers, but the general meaning is the same. So i- deformation is independent from the scale. Okay, shear zone is made in this way. You have undeformed protolite, undeformed protolite. This part is displaced to the right. In the shear zone, you can develop a foliation like this. Above the foliation, you can see elongated crystal or minerals or deformed objects. And the foliation became stronger and the shear zone going towards the center of the shear zone. Usually, the best description in mathematical terms is assuming that the rotation axis epsilon is this one, and the epsilon is equal to 1. So this is the condition that is named the plane strain. So you have deformation along the x-axis and the z-axis, shortening, elongation, with no deformation along this axis. Also, the axis of rotation, that is monoclinic flow, because the axis of rotation is oblique. You have a triclinic deformation, but it is very difficult uh, to deal with. But in some papers that we made with Case Pasquier and my former students Jacopini, we found with numerical models that increasing the deformation, you can start by triclinic deformation, but with increasing strain and time, deformation became monoclinic. So in very high strain shear zone, the assumption that rotation axis is this one is almost correct. If deformation is low, it's a problem, but with a very strong increased deformation, this assumption keep. Another important thing, you have defoliation stretch inclination, marking the x-axis. And this plane is the plane where we can observe the foliation, the shear zone, and the kinematic indicators. It is the XZ plane of the finite strain ellipsoid. You can observe kinematic indicators only in this plane because in other plane you can observe the component of the formation. So you can you can have you can have not the right information about the sense of shear. But it is very important to have the right sense of shear in geographic coordinate because you put if you put on the map this right sense of shear that is top to the northeast, if you have a cut in this direction, you can have a component to the north, and you can put the wrong sense of shear on the map. Okay? This is just a movie from Fossen. There is a website of the Book of Fossen where you can download this kind of movie pictures. It's very useful. Here you can see the shear plane, the deformed object, projection of lineation on the shear plane, and you can see that the object became much more stretched. Oh, è andata avanti. Okay. The object is much more stretched and rotate towards parallelism to the shear zone. Is shown also in this picture. You can see the shear zone is growing, displacement to the right. The shear zone starts in this small part and then increase in thickness. The deformation is represented by these green ellipses that become more stretched in the central part of the shear zone. In this graph, you can see the gamma, the shear strain, that is related to the amount of shear, and the angle theta prime, that is in between the x-axis of the strain ellipsoid and the shear zone. And the angle starts at 45 degrees in simple shear, and then decreases a lot, became parallel to the shear zone boundary when the gamma is much more larger than 10. Okay, so the strain ellipsoid became more elliptic, an isotropic shape, and rotate a lot to parallelize to the shear zone boundary. And this is the matrix of the formation in two dimensions. Gamma in this position means that the formation is like this. So no displacement along the vertical axis. So it is just to remember that in this kind we speak about heterogeneous shear zone because the shear strain changes along the profile. The shear strain has a amount different from here, 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 and here. So the displacement is is calculated by this integral between the thickness of a shear zone in considering the strain, the shear strain, or you can uh, sum the along the profile. So usually the formation is a classical heterogeneous in the shear zone. It is very rare to find homogeneous deformation in the shear zone. They change a little bit continuously. I have never seen a homogeneous shear zone in my life. Theoretically is possible. In this picture that you can find in the book of Fossen, but also In the review, you can see a small shear zone from Adamello. Uh, this is the thickness of a shear zone. And along this profile A, B, and C, you can find a different amount of displacement calculated by integral. So the heterogeneity is not only in this position, but also along the shear zone. Just at a small scale shear zone because it is 12 centimeter. In this graph is referred to this picture. You can see the shear zone, the extra shear zone, a dike entering these positions and displaced this way, a dike entering at 90 degrees and displaced by the shear zone. Uh, so you can observe different behavior. R is the axial ratio of the strain, finite strain ellipsoid, x over z, this one, and with increasing strain, the axial ratio increase continuously uh, with increasing shear strain. The angle theta prime decreases from 45 up to tend to parallelize to shear zone with increasing the shear strain. But you can give a look to the angle. Uh, beta 2 is this one. Beta 2 means a dike entering the 150 degrees to the shear zone and then rotate to parallelism to the shear zone. The same behavior is from a dike entering at 90 degrees perpendicular, then deformed, transported by the shear zone, and then going outside in this part. Also in this case, the formation tends to parallelize this angle to the shear zone. So the shear zone is an attractor because all the lines tend to parallelize to the shear zone. Mm. The only thing that increase it is the axial reaction because increasing with gamma, the axial ratio of the strain increases up to the maximum in the middle part of the shear zone, in the center of the shear zone. Okay, this is a movie showing what I have. Already. In this picture, you can see the progressive simple shear is increment by increment. The deformation increases up to the maximum shear strain and maximum elongation of the object and the rotation of the axis towards the shear plane. In geology, in the field, a gamma like 10 is very high. You can recognize easily uh, the angle of foliation and the shear zone because when you are in a field, more or less this foliation could be up to gamma 6, 8, 10. Then you can see a foliation parallel. And with the compass, you can have the enough sensibility to measure an angle less than 2 degrees or 1 degrees. So after gamma 10, it is very difficult to observe it unless you take a sample, you cut in the laboratory, and you study. Since actually you can detect also angle below 1 or 2 degrees. Okay, I think we can stop. It's 1 o'clock. So, okay, we continue this after lunch. I will show you the fabric development along a shear zone with increasing strain and so on. Okay. Have you some question? It's okay. I am going too fast or too slow? It's okay. Mm. Va va bene. Thank you. Mm. Okay.